All right, hello. I call these next 2 or 3 lectures the basics, but it should really be called an advanced review because I do expect you to have had 4 semesters of chemistry, so you should have a good understanding of the periodic table, electronic configurations, and periodic trends. However, I'm going to dig a little deeper. Yes, maybe I'll bring up some topics that you already know, but I'm going to dig a little deeper, explain things in more detail, and hopefully you'll gain a better understanding of why things are arranged the way they are in the periodic table and what do we do with this. So let's get through these basics so we can look at the advanced topics such as symmetry, organometallics, and dynamic NMR. I really look forward to talking to you about those things. We all know the periodic table. This one doesn't have any elements, but if we are investigating into the makeup of it and related to the energy levels as we discussed for quantum mechanics and some of the electronic configurations where the electrons are and what orbitals, then it is very useful to look at the periodic table in terms of blocks. So you should know and be familiar with these blocks here, right? The main group, this is the main group here, the S and the P block. And you could take out the D's, combine them together, and you could call that main group elements. And so it's important that we remember that this is P, this is S, this is D, and then down here we have F. And then another interesting or a really important thing to remember is, and I kind of wrote over it here, but we have 1s, 2s, 3s, 4s, 5s. But after the 4s, we are actually inserting the 3D. So this is where we start the 3, and this is where we start the F, right? So we are inserting the lanthanides after the 6s. So when we do electronic configurations, it's useful to keep that in mind. It's also important to understand that the periodic table is really supposed to look like that. We've taken the lanthanides and actinides out, this F block here, so after the 6s here, we are actually filling the 4F, and then when you're done with it, we continue filling the 5D. So that can be a little bit confusing, but all you need to do is look at the periodic table when you do electronic configurations. Remember the blocks, right? This is S, this is P, this is D, this is F, and remember that this is where the 3D starts. Remember, this is where the 4D starts. And so all you have to do is follow the atomic number, right? You realize that after 57 we have this gap, so that means we got to come down here. And you can do electronic configurations of anything on the periodic table. But obviously we're not just going to follow Aufbau, which is the order in which the electrons fill. We're going to look at ground state, and that's really the important part. We're going to look at elements in its ground state, not the way they fill the orbitals. Okay, so let's just do an example. Let's do, I don't know, vanadium. So all you need to do is follow the atomic number. Start with 1. That's up here, right? So also didn't mention, in addition to the blocks, you also need to look at the periods and the principal quantum number, the energy levels 1, 2, 3, etc. So if we're going to do vanadium, it starts here with atomic number 1. That would be a 1s orbital, right? You're in the s block, pretty easy. Maximum capacity 2, so it's just 1s2. You fill it, you come over to the next block, come over to the next atomic number 3. That's again, we're in the s block. This is the second period, so it's 2s2. You follow the atomic number. This is now the P block, so this is a 2p. It's full. We're done. We're at neon. Coming down to the third, so it's 3s2. And again, we get over to the P block. This is the third period, so it's 3p6. Then we fill the 4s, 4s2, and then this is the 3d, and there's 1, 2, 3 here. So this is then the 3d3. And again, this is just Aufbau. And what happens when you do the ground state, logically the lower number is going to switch with the higher number. So the 3d and the 4s are going to switch in energy, and I'll explain that or I'll try to explain that in a minute. But it's important for us to understand that 3D electrons are lower in energy, and so when we engage in ionic bonding, it is the s electrons that are the first ones to go, and that explains why most of the transition metals have a oxidation state or charge of plus 2. It is these s electrons that are removed, and then occasionally we can remove one or two or more of the D's, right? So just follow that. Let's do one more example. Let's do something more crazy. Let's do erbium down here. Shouldn't scare you. So basically, you're just gonna follow the line here. Let's see if I can actually do it. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and so I didn't memorize that. Well, I kind of did, but all I'm doing is, again, it's like this is the 1s, this is the 2s, this is the 2p, this is the 3s, 3p. I'm just following that 4s, and then technically that switches the 3d, but we're gonna leave it alone because we're not looking at valence electrons, so it's not really all that important. So then 3d, and I come back out, and this is the 4p, so I'll continue. 4p6, I keep going. 5s2, and then again I'm going to fill the 4d10, 5p6. I hope I don't run out of space. So I'm here now. 5p6, coming to 6s2, and now I got to watch out. This is where the lanthanide series starts. So I'm going to insert and take a look here. We have 57, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm going to go 4F12, and I'm going to hope for the best that this is correct, right? So that's all it is. Very easy. You don't really need to do this crazy thing you may have learned in high school or in your first general chemistry course. It's a nice little bridge that can help you memorize and figure out which orbitals fill first, and the order in which the electrons populate these energy levels, right? So it makes sense. It goes from lowest to highest, and so it might be a little bit more useful to look at the relative energy level of these orbitals here. They are color coded, which is nice. We have the D's, the third energy level, fourth, fifth, all together. And so notice this weird overlap here, right? I mean, this is how the periodic table is arranged. We've got these, we feel the 5s, and we just did that for erbium, right? Or whatever I was doing there. 4d, and then 5p, so we kind of zigzag. And so what's that all about? But the important part is that it makes sense that the first energy level is filled, then the next one, and the next one. And so what happens when you get to the 4s and you put an electron in here? As you populate or put electrons into these levels, the energy changes, right? So the more electrons you put into an orbital, the lower the energy. And so see, these are so close in energy to begin with, and all it takes is for one electron to go into this 3D level, and it'll drop in energy below the 4s. And that is why in the ground state that the 3D is lower than the 4s. And it shouldn't be hard to grasp that or memorize that, because 3 is a lower number than 4. You just have to remember that the 4 fills. And then you fill the 4p, and then the same thing happens again when you fill the 4d. It drops in energy, and even the 4f is going to drop below. The 4f also drops below, and so those go up in energy. This is the same chart, not color coded, but it has the levels nicely separated. And so again, the 3d will drop between the 4s and the 3p. Okay, not really a big deal, but important when it comes to electronic configurations in the ground state, and then it really will help us determine the oxidation states and the bonding and the behavior of these elements. All right, so when we do electronic configurations, there's a couple rules we need to follow. Pauli exclusion principle. We already had an entire lecture on quantum numbers. So each electron has to have a different space at the same time, right? They cannot overlap. It's just not possible. They have to go in different orbitals, and if they're in the same orbital, they have to just go in different directions, so they don't bump, they don't occupy the same space. Makes sense, right? Hund's rule is about spreading out the electrons, or it's about that ground state and lowest energy, the desire of electrons to be in the lowest state possible, right? And so by spreading out the electrons, you are accomplishing that. And so you probably did looked at orbital diagrams. So if you do, for example, if you look at something like phosphorus, which has 5 valence electrons, and so you pair them up, and then when you go to the next one, the third and the fourth and the fifth, you spread them out before you pair them up, and that's following Hund's rule. And so by pairing costs energy, right? So there's and also breaking this up again, right, costs energy. And that's an important principle to look at, that spreading out the electrons leads to lower energy and the ideal or preferred ground state of these elements. So let's take a look at some of the exceptions. We already highlighted that this is not what we do. Aufbau for nickel, the ground state for nickel is 3d8 and then 4s2, and when nickel goes to nickel plus 2, we know it's the s electrons that were removed. A little later on, we will look at effective nuclear charge, which is how strong does the nucleus pull on a certain electron. And we're going to calculate the effective nuclear charge for the 3d electrons of nickel and the 4s electrons of nickel, and you'll find that the 3d electrons are held on stronger than the 4s. So this is all connected. All of those periodic trends and all of those characteristics are connected to atomic radius as well. And then but really important that you follow that. So there's some crazy funky exceptions, like lanthanum will actually fill 1 in the D and not. It starts off the lanthanide series, but it's really just as a transition metal. Let me see, I'll show you where that is here, right? So lanthanum is this one, and so lanthanum is listed here as if it had the 4d1 electron filled, and it does, and then after that we fill up cerium, but we call this the lanthanides, right? And so that's a little interesting here. And when you go to the next one, and that's an odd exception here. It keeps the d electron and then has 1 in the F, but after that, so then praseodymium, we then promote this d electron, and so we have 4f3. So that's an odd exception, probably not all that important. So when we go to lutetium, then obviously we have to have that extra electron, so that's 14 plus 1, and so you see the 14F as well as that 1 in the D, and it's correctly ordered. It's 4, 5, and then 6. All right, again, use the periodic table to do electronic configurations, SPD, and all those exceptions. And so let's take a look at some of the more important exception for electronic configuration. We have the group 6, which is chromium, molybdenum, and tungsten. So we are looking at, let me go back and show you, those are the ones. And so of course, for the ground state, we would expect it to be 3d4 and then 4s2, but that's not the case. And the reason that chromium and molybdenum does this, and take a look, tungsten does not. So there's an exception within the exceptions, right? But you can explain this by, we have a half filled orbital here. We have a 3d, if you draw it out, we have 1, 2, 3, 4, 5, 6. All of the electrons are spread out for the electronic configuration we expect. From Aufbau, we would have one paired up and then a single empty D. And so it is electronically or energetically favorable to have them all spread out, and this is why chromium and molybdenum do that. Okay, so the other group where we have an exception is when we go to copper, silver, and gold. And you may recall that silver is one of the exceptions when it comes to naming. We don't have to give a Roman numeral. Silver is always plus 1, and so that is reflected here in this exception. And we also know that copper is 1 and 2. Those are the common oxidation states, whereas most of the other transition metals have a +2 oxidation state, not a +1. So iron is +2 and +3, and so most of them do have this +2 and then one more. And copper and silver and gold as well, all three do this, and that's obviously because there's an energy benefit from filling the entire D shell and then just having a single electron in the S. It's almost like a pseudo noble gas, right? So it's like it has a full 3D shell. We call the zinc electronic configuration a pseudo noble gas because it has the 3D full, and then they will become completely inert. But we also know that copper can also be +2. So copper is not one of the exceptions, and if you do name copper compounds, we do name them copper 1 sulfate and copper 2 sulfate, not just silver sulfate, which would imply a +1 oxidation state. Okay, speaking of oxidation states and charges, so here's this exception here, right? We know that silver is always going to be +1, and we expect zinc to do the same. It has a full shell, and so not much needs to be said here. Just a little bit of a reminder, this is for ionic compounds. Here are, and that might be interesting, I just already mentioned that most of these oxidation states are +2. And that's true here, right? This is the 3D series, and electronic configuration is shown here, right? They even have the exception for copper shown. They have the exception shown for chromium, and you might expect chromium to have an oxidation state of +1 because of that, but it's as if you have 6 orbitals all on the same energy level with 1 electron, so it actually will lose all 6 of them. Look at that. Chromium is one of those crazy ones. Look at manganese, +7. Right, interesting trend here, right? So in the middle, we are likely to lose. We can lose a high number of electrons, but so it still holds true that a lot of common oxidation states of all of those is +2, and then there's a couple of them that have, of course, these exceptions. All right, moving along to the periodic trends. So I'll save that for the next lecture, but so this is something we're going to be calculating effective nuclear charge in the next lecture, and that is something that is most likely completely new to you. But anyway, that's enough for a short little introduction to the periodic table. I'll see you in 5.